Over the past few years, while creating video content, the author has noticed that many viewers, often unconsciously, hold on to common cosmic myths. To address this, he set out to debunk these misconceptions and shed light on the true nature of things. When someone watches the sky at sunset and sees the sun, what color do they typically assign to it? Most people would probably say yellow, orange, or red. Indeed, in countless illustrations and animations we encounter, the sun is often portrayed as a giant yellow ball of glowing plasma. However, the sun is not actually yellow. It emits light across all visible wavelengths of the electromagnetic spectrum with nearly equal intensity. This means the sun is just as violet or green as it is yellow. When all these colors combine, they produce white light. Therefore, the sun is, in fact, white. But if the sun is white, why does it appear yellow or even red in our sky? This phenomenon is due to Earth's atmosphere. Blue light has shorter wavelengths than red light, and shorter wavelengths scatter more easily off molecules in the atmosphere. As a result, red, orange, and yellow photons from the sun pass through the atmosphere relatively unimpeded and reach our eyes directly, while blue, green, and violet light scatters away. That's why the sky looks blue and the sun appears yellow. Many people have heard of the so-called dark side of the moon, perhaps thanks to Pink Floyd's famous album. In reality, however, there is no such thing as a permanently dark side. This misconception particularly frustrates the author. The moon is tidally locked to Earth, meaning it rotates on its axis at the same rate it orbits our planet. Consequently, we always see the same hemisphere. That's why the moon looks identical night after night. The far side is fully illuminated during meta. Interestingly, this hidden hemisphere offers advantages. Astronomers have proposed building a radio telescope there, using a crater as a natural dish. Such a location would be ideal, shielded from Earth's radio interference. Next, the author shares 3 quick facts he aims to deliver in under a minute. Ready? In movies, flying through the asteroid belt is often depicted as a chaotic, high-stakes maneuver requiring constant dodging of massive rocks. In truth, asteroids are so widely spaced that the chance of colliding with one is less than 1 in a billion. Space missions don't even account for this risk during planning. Another common claim is that the sun is a fiery ball burning in the sky, but that's inaccurate. There's no fire in space because there's no oxygen to sustain combustion. The sun's heat and light come from nuclear fusion in its core, not chemical burning. Finally, many assume Mercury is the hottest planet because it's closest to the sun. Actually, Venus holds that title, with surface temperatures reaching 465 degrees Celsius, hotter than Mercury's 430 degrees Celsius. This is due to Venus's thick atmosphere, rich in carbon dioxide and sulfuric acid clouds, which creates an extreme greenhouse effect. Here's another intriguing point. Black holes don't suck things in. Despite popular depictions of them as cosmic vacuum cleaners, they're simply massive objects with intense gravity, much like stars or planets. To illustrate, if we replace the sun with a black hole of identical mass, Earth's orbit would remain unchanged. After 8 minutes and 20 seconds, the time light takes to reach us, the sky would go dark, but gravitationally, nothing would differ. We continue orbiting the black hole just as before. This principle actually helped astronomers detect Sagittarius A, the supermassive black hole at the Milky Way's center, by observing stars orbiting. Another widespread myth claims nothing ever escapes a black hole. While it's true that nothing inside the event horizon can return, not even light, this isn't the full story, thanks to Stephen Hawking. His theories show that black holes aren't perfectly black. They emit a faint stream of particles known as Hawking radiation. Over immense timescales, this radiation causes black holes to lose mass and eventually evaporate. This process stems from quantum mechanics. What we call empty space isn't truly empty. It's filled with quantum fields. According to quantum theory, particle-antiparticle pairs, like electrons and positrons, constantly pop in and out of existence. Normally, they annihilate almost instantly and remain undetectable. But near a black hole's event horizon, if one particle, with negative energy, falls in while its partner escapes, both become real. The escaping particle becomes Hawking radiation, while the infalling one reduces the black hole's mass. Though this energy appears to leave the black hole, the process takes billions of years, and anyone already inside could never escape. Another common misconception is that space is a cold, icy void. In reality, space has no temperature. Temperature measures particle motion, and in the near-perfect vacuum of space, there are too few particles to define a meaningful temperature. How hot or cold you feel depends entirely on your location. Near a star like our Sun, you'd absorb intense radiation. Astronauts in Earth orbit experience temperatures up to 250 degrees Celsius on the sunlit side and as low as minus 250 degrees Celsius in shadow. So space isn't inherently cold. This leads to another myth, that a person exposed to space without a spacesuit would instantly explode. In reality, the main danger is the lack of atmospheric pressure. Air in the lungs would rush out immediately. Oxygen in the blood lasts only about 20 seconds before unconsciousness sets in. Then, bodily fluids would begin to boil due to low pressure, causing swelling. The body could double in size, but not explosion. Survival might last up to a minute, but not longer. You've likely seen images of comets with bright tails and assumed the tail points in the direction of motion. Actually, the tail always points away from the sun. Solar radiation heats the comet, releasing dust and gas, and solar pressure pushes this material outward, forming a tail that streams directly opposite the sun, regardless of the comet's travel direction. Contrary to belief, space isn't entirely silent. Sound requires a medium like air to travel as pressure waves, and the vacuum of space lacks such a medium. So, yes, most of space is silent. However, regions with gas and dust, like around black holes, can transmit sound. NASA has even sonified data from a black hole, producing an eerie sound. We should be grateful space is mostly silent. If sound traveled as easily as light, the sun would roar louder than a jackhammer, and we all be deaf. Many think time is a universal constant, but Einstein showed otherwise. His theory of special relativity reveals that motion affects both mass and the flow of time. A fast-moving object experiences time dilation. Time slows down relative to a stationary observer. Astronaut Scott Kelly spent nearly a year on the ISS, orbiting faster than his twin brother Mark on Earth. Due to time dilation, Mark aged about 5 milliseconds more. The ISS moves at just 0.0026% the speed of light. But if Scott had traveled at 99% light speed for 5 years, Mark would have aged 50 years. Thus, time is not absolute. Many also mistakenly believe the moon's phases are caused by Earth's shadow. In fact, phases result from the portion of the moon illuminated. Only during a lunar eclipse does Earth's shadow fall on the moon. This is a separate phenomenon. Finally, there's a subtle but important point about light and gravity. Since photons are massless, some assume gravity doesn't affect light. But gravity warps space-time itself. Massive objects like black holes or galaxies curve space-time so severely that light, traveling in straight lines through this curved geometry, appears to bend. This effect, gravitational lensing, allows astronomers to observe distant galaxies whose light is magnified and distorted by foreground mass. It's also one of the few ways we can detect stellar mass black holes.